Thank you guys for being here today for this seminar, periodic seminars. Today we have a talk by Benny, a senior researcher from the lab. He's talking about towards certifiable resource sharing in safety critical multi-core real-time systems. So Benny, you have around 45 minutes to entertain us.
Thank you very much for the kind introduction. It's my pleasure to be here and to talk to such a distinguished audience of colleagues. So this presentation was actually originally developed for a workshop on certification of multicores that was co-located with our task. And then yesterday I went with Eduardo to Lisbon to attend the Ashley workshop, and we were invited to give a presentation on similar topics. So I recycled this yesterday, dusted it off, brought it back into the working set of my brain, and then I thought, well, if I'm gonna bring this presentation back into my mind, I might as well also present it here locally, because I never shared this story with you before. So that's what I'm gonna do today. And this presentation is not about my work specifically, but more about a research area and talking a lot about what other people have been doing and what the research community in general is doing. So it's a kind of presentation that has a lot of references in it that can serve as pointer to other work in case you're interested. And to help me out with this presentation, I also had some input from Jan Novoc at Airbus because parts of this relates to the work that he's been doing. Okay, so I'm going to start this presentation like I start all the other ones about complexity and complexity trends. Here talking first about embedded systems in general, that we get increasingly complex systems because there's more functionality, so the application gets more complex. There is more applications in the system, and there's more of those running concurrently at any given time. And this is a very general trend. You can see it in a lot of different industrial domains. You see it in consumer electronics because you have this convergence of application domains over the past 10 years, where what used to be then a digital assistant or an MP3 player, all of these gadgets turned into one single tool called the smartphone that just does all these things for us. But you also see these kind of trends on the automotive side. So in the past, there might be, well, hardly any computers, then some computers, and then as we're going towards increasingly sophisticated driver assistance systems and ultimately towards autonomous driving, it just means more and more functionality, more and more sensors, and lots of computation. So that's another domain that has a similar trend, although maybe for a slightly different reason. So because of this means that we need systems that can offer just more and more performance all the time, but they must do that without increasing the general power consumption or the general size of the systems, and so on. So as a result, there's been this transitions from single-core systems towards multi-core systems, maybe even heterogeneous multi-core systems in some cases, to improve this general performance to power or performance to size ratio that's desirable. And one feature of these systems is that resources are shared to help reduce the cost. So looking more specifically then at safety-critical systems, you have systems, applications that are real-time requirements. And I don't think I need to explain what real-time requirements are in this particular room. But in addition, you start having applications with different safety levels, different criticality levels. And exactly what they look like depends on the application domain. They have different names and letters in the automotive versus the avionics domain. In avionics, these are called design assurance levels, or DA levels, and they go from A, that's the most critical, to E, that's the least critical. And then among the DA level A applications, you find, for instance, cockpit applications like display autopilot. You also have other critical systems that can be A level, like flight control or engine control. And then you see a gradual decrease in criticality level based on what the consequences would be if that system would be failing, as if it could bring a plane down, or if it would just could cause injury to passengers or cabin crew, or if it's considered non-critical, where you have, in this end, the systems that are aiming towards you guys, towards the passengers in the airliner, for instance, where we have an example of in-flight entertainment. If it does fail, and it has happened probably to all of us at some point, it's not really fatal. except the possible chance that you'll die of boredom during a long-haul flight. So it's not so bad. What's interesting about these DAW levels is that the higher the DAW level, the longer it will take to develop the application. The reason is that if you look into these certification guidelines for software and hardware correspondingly, you will see the different processes that they require and all the things you have to do, and it's several pages of process you have to follow for a DAW level A application, and as the criticality decreases, some of these steps can be omitted. So it's about how much, what kind of traceability there has to be of requirements, how much version management there must be, what you must store in terms of evidence during development and documentation for the process, how many independent developers that must be involved, or how many independent implementations there must be of the same functionality, all these kind of things. So as a result then, if you have applications with high DAW level, that means it'll be very, very expensive to develop, and it'll be very time consuming to verify and to certify. So this is a very sensitive issue in terms of development cost. An interesting thing about these systems as well is that there's this drive towards using commercial off-the-shelf platforms. The main reason is that although when you're at the airport and you look around, you see a lot of airplanes there, the kind of volumes you're talking about for these systems are still fairly small if you compare it to the number of smartphones. So it's maybe not so interesting to start developing custom hardware IP specifically targeting airplanes if it's just in a computing system, because then you have to amortize the cost of that development over a fairly small number of units and a small number of produced chips in the end. So if you combine this safety thing with increased integration, then you can arrive at the point where you need to integrate applications with different DAW levels in the same systems. And that's when you start to get mixed criticality systems that I'm sure you've all heard about in the past. So that's when things start to get really interesting. In particular in the context of resource sharing, because when you start sharing resources like cores or interconnect or memories, then you start getting interference between applications and you make their whole timing behavior interdependent. And then all of a sudden it gets pretty difficult to determine the worst case execution time of the application and has to see if all the deadlines are satisfied. There is an additional requirement when resources are shared, and that is that if you have applications with different levels sharing a resource, then all of those applications must be certified according to the most critical DAW level of all those applications. So if you have one level A application sharing resources with a level E application, then all of those have to be developed and certified according to a level A process. So then a system that should be fairly cheap and easy to develop becomes very, very expensive because it has to follow this very rigorous process. So having isolation then between applications of different criticalities becomes very important. And you need isolation in a number of different ways here actually. You need both temporal isolation and spatial isolation, where temporal isolation means that the timing behavior of one application must be independent of the others, and spatial isolation means that they can't interfere with each other's memory space, for instance. So one application cannot corrupt the data of another or read the data of another, so they should be independent also in that sense. I've grayed out spatial isolation. I did that here not because it's not important, but I did it because I'm not going to talk much about that in this presentation. I will focus on timing aspects. There's much more work that has happened on timing aspects, particularly in the real-time community, because that's what we like. But there are also people working on aspects of the spatial isolation with memory protection units and so on. But we won't talk about that. When it comes to isolation, you can also always ask yourself, well, what does isolation mean? How isolated and independent do things have to be? And there's a great answer to that question. They have to be sufficiently independent, where sufficiently depends on the particular system, the particular product, the particular maybe certification authority. So there's no clear answer. Certification authorities are not telling us what sufficiently means because that would be a liability issue for them. Companies are not going to tell us what was sufficient for them in their particular certification projects because they'd rather not say what kind of evidence they're producing. So it's a bit it's a bit vague. So isolation is important. So how do we achieve isolation? What are people doing? Well, on the single core, this is very well worked out, because then you have isolation being provided by the operating system or a hypervisor layer. So you can base this on something like the ARINC 653 interface or specification that says that you should build your system with partitions, and you will do that by having, in this case, I have 2 partitions in my figure. Each partition has 2 applications, and maybe these are very critical applications, and these are very non-critical applications. And then those are being scheduled using time division multiplexing. So there's just a static schedule that says partition 1 during this time, then partition 2, then partition 1 again, then here is an empty slot. And during this empty slot, even if one partition would want to execute, it's just not allowed to, because it's non-work conserving application. There is no slack exploitation or opportunistic scheduling. If it says no, it is no, because we want to know exactly what's going to happen. And then inside a partition that is executing, you can use a task level scheduler here, like fixed priority or EDF, to schedule the actual tasks. So this is how they do it with ARINC 653. Okay, so looking forward at what we're going to do in this presentation then is to see, well, how can you then ensure that applications that are sharing resources are isolated, and that the worst case execution time of those applications can be determined in a certifiable mixed criticality multi-core system. So what happens when you go multi-core with this problem? And this will then be a survey of different approaches and different things that people are doing. We're going to approach it in the following way. So I'm going to start by looking at what can you do if you build your own hardware. So how can you find hardware solutions to these problems? Secondly, what if you can't? So the hardware is just given to you and you have to analyze it or come up with software solutions on a touch platform. Then what do you do? Then I will talk very briefly about the Airbus approach and what they are doing, what their flow looks like, and draw some conclusions. So this story is probably familiar to you, because this story I've been talking very extensively about in this group in the past. It's a couple of years ago, so maybe all of you didn't hear it, and I will only explain a very small subset about the ComSoc platform now. But the ComSoc platform is a platform that is being specifically designed for real-time application, built bottom-up from scratch to be analyzable and to enable applications to be developed independently, verified independently, and allows them to execute independently with complete isolation. So at the very high level, the ComSoc platform is a tiled architecture where there's some processor tiles then that has some microBlaze processors and a bunch of small local memories. There's some memory tiles that support SRAM and SDRAM memories. That's been the scope of my research primarily for the past 10 years. There's some peripheral tiles with audio controller, display controller, these kind of things. And then this is all nicely tied together by the network on chip, which is called Ethereal. So the ComSoc platform has its root originally in Philips in NXP, but is currently maintained by Eindhoven University of Technology. And there's a System C simulator for this, but there's also VHDL implementation and platform instances that are generated on FPGAs, and it's used in Eindhoven quite extensively for both education and for research. So what's interesting here then, in the context of this story, is that all resources in this platform are shared. So the processors are shared, the network on chip is shared, and the memory controller is shared between, well, in this case, different partitions with different criticalities. So the techniques that are being used here then is that for the processor sharing, it's using time division multiplexing, non-work conserving scheduling to schedule the partitions. So it will be just the same way that is done in the ARINC 653 specification. For the network on chip, well, it's kind of the same trick again. It's again TDM schedules, but now since it's a multi-hop resource with many routers, it'll be this kind of pipeline TDM scheduling instead. But it's again TDM and it's non-work conserving, but this one is then working with network flits instead. And for the memory controller, well, if you have a winning concept, why don't you just stick to it and use non-work conserving TDM transaction scheduling, because non-work conserving TDM is a good way to eliminate interference. But there is actually an option for this particular resource where we say, well, if you have any transaction level arbiter that is predictable, so you can bound how long it takes before your particular transaction will be scheduled. So if it's round robin or fair queuing or whatever predictable arbiter there is, then we have a little hardware block that you can program with the worst case response time, and it will just wait until this worst case response time and release requests. So then you can use whichever predictable arbiter you want, and you'll always see the worst case performance. So you are going to be independent of what everyone else is actually doing. So I want to mention that because this might be important to distinguish, CompSoc cares about independent timing in terms of actual execution time, not just about bounds. So that's something that's interesting to see. So that's then a platform that was built to be analyzed, and that's a big part of the work. But another part of the work is, of course, to do that analysis. And the CompSoc platform is primarily built for data flow applications. That was the origins of that platform. And it has, the analysis is primarily based on data flow analysis as well. And that means that you have data flow models for your applications, has to be provided as input, but there's also data flow models for all the components, for all the hardware components and all schedulers. So there's data flow models then of scheduling on cores, of network on chip, of memory controller, and the memory controller scheduling, and so on. So that means that if you provide your simple data flow graph as an application input, once that has been mapped to the CompSoc platform, then this graph gets extended with all sorts of extra nodes and edges to capture how it will behave mapped on the particular platform. So then to take into account all delays in network, in memory controller, in the DMA, and so on and so forth. And then as a result, a simple application like this turns into this giant graph full of information about what the hardware is doing. And if you analyze this, you get fairly accurate bounds on the throughput that can be guaranteed for that application. This can then be verified on an FPGA and has been in this publication. Actually, not in that one, in another one that's not listed here. So in terms of partitioning, it provides what I would call extremely robust partitioning, because it's a fundamentalist approach to isolation, where if an application runs independently or together with another application, you will see 0 clock cycles difference in when output's being generated. In fact, you can even probe inside the platform and you can show that this transaction is issued inside the network on the exact same clock cycle, no matter if you're executing alone or with someone else. Thanks to this hardware delay or this non-conserving scheduling, you just don't notice if there's anyone else around. And that is something that we've demonstrated in a demo many years ago, and I think maybe I even showed that demo here, where we have, and you don't see this picture very well, there's this video decoder here, H263, that's running on 2 cores, and we're measuring the time at which each macro block is being finishes decoding, and we do that when the application runs alone, or when it runs with another instance of the same decoder, also using the same 2 cores, and that's in a picture-in-picture setting, and the timing behavior is completely unchanged. So that's something that the CompSoc platform can do, but it's not the only platform that has been thinking in these directions. So for instance, the precision time architecture, the PRET project, proposed by or run by Berkeley, they're doing very similar things about having repeatable timing behavior of applications, but they're using slightly different techniques in their resource sharing. So the conclusion from this part of the presentation is, well, if you want to design time predictable hardware that provides extremely robust partitioning and provides worst case bounds for every transaction, for every task, then you can do that. It has been done, it has been demonstrated. There are drawbacks with this kind of approach though, and that would be something like the average case performance. That suffers, of course, because if the mantra I keep telling you is non-work conserving scheduling, don't exploit any slack anywhere in the system, or if anything would go faster than it should, slow it down to the worst case response time, well, people that do care about average case are going to start frowning. So that's a problem with this kind of approach. A problem also in the context of the particular story I'm telling about avionics is that they're practically restricted to COTS platforms, as I mentioned before. So the hardware is given. So you can't build your own, you can't afford to. So then they need all of this technology built into the COTS platforms that they buy. But of course, it's not very easy to come with revolutionary hardware built on new concepts and say, hey, Freescale, manufacture this, because, well, they may not want to, and they will look at it not just from a technology point of view, but they will start looking at market shares and probably say, there's pretty few people in the world that actually want this. Most people want the average case performance and not necessarily the isolation. So I'm not sure it's going to be good business to manufacture this chip. So that's hard, because in the end, there's quite some people at a real-time conference, but you need very, very large volumes to manufacture it. So let's see, what can you do instead then? You can try to get your COTS platform and model it and analyze it the best you can. The problem you're going to run into, though, is that, first of all, the COTS platforms that you get, they're optimized for the average case performance because that would reflect the interest of the average customer. And another problem is that the documentation. Well, there is a lot of documentation. You'll get like 5,000 page reference manual. I mean, those of you here working with the Calibrate probably have seen that. And then they'll be telling you exactly how the memory mapping is of every single register. But then when you're reading it as a researcher and say, yeah, what does it really do? You realize it doesn't say how any scheduling algorithm works. There's no algorithm, and there's no high-level description even. It's just not there. It's not an accident. It's most likely due to IP protection reasons. So you're gonna have to start guessing then and see what you can do. And you can say, well, maybe we'll reverse engineer it. And then you run into another problem that, well, if you have just a hardware chip like that, it's very limited observability. There's not a lot of places where you can measure, you can probe, you can try adding some printf statements every here and there, but that's hardly enough to reverse engineer what a scheduling algorithm is really doing. So it's hard to model the behavior of a COTS platforms, the individual resources, and even if you do come up with a model, it's hard to convince anyone that that model is correct, and for sure you won't be able to say, I know for sure that it's safe. So you're going to see a lot of pessimistic assumptions, and I'm going to present some of these in the context of memory controllers here, because that's what I'm most familiar with. So what people do, for instance, is to say, well, in a memory controller, a commercial memory controller, they want to optimize average case performance. And what they do is they just collect a whole lot of requests in a reorder buffer, and then it will serve them in the order that best optimizes throughput. Then, of course, the question is, what's that going to do to your worst case? Well, that depends on the size of that buffer. How many requests does it have to choose from? If that's really large, there's a lot of options, you may have to wait a lot longer. And you know that buffer is in there somewhere, but you don't know how big it is. So what number are you going to guess? If you guess too small, then your bounds are going to be, they're going to look nice, but they may not be safe. If you guess very large or infinite, well, then your bounds are going to be very, very ugly. So yeah, that's a problem. When it comes to scheduling algorithms in memory controllers or buses, then you can say, well, I don't know if it's TDM or round robin or something priority based. But what I can know is that it's probably something that's worth conserving, because if you want to optimize your average case, you're going to use all the slack you have in the system. And then you can base your analysis on that, saying, I just know that if there's 1,000 requests from everyone in the system, 1,000 requests later, my request will be served. I don't know anything about the order. Maybe I will in fact be first because I have high priority, but I don't know that. I don't know if this guy cares. So you can just use this word conservation assumption and you get numbers out. The question is, are those numbers then useful, or are they going to be so large that no system would meet its deadlines? There's been tons of work going on bounding interference between tasks. We've done quite some in this group even. And you see all sorts of flavors depending on which particular task model people like. Is it periodic? Is it sporadic? Is it a task graph? Or what kind of schedulers are looking at for the resources? Is it TDM, round robin, or pair queuing? And you get all sorts of different flavors. So it's not interesting maybe to talk about each of these works separately, but it's interesting to see what are the common assumptions that people are making and say, well, what do we think about those? And one that's very common is to say, we assume that there's a single outstanding transaction. So a processor issues a read request and it will block until the response comes back. or it issues a write request and it waits for some kind of acknowledgement before it continues. Because this means that you can just have your worst case execution time and all the interference for resource accesses are just additive, and it's very, very beautiful way to do analysis. But unfortunately, it's not really true because, well, as you want your embedded processors to become increasingly powerful to deal with these applications that we're talking about, and you want to optimize the average case performance, anything that's not a very simple microcontroller, so any sophisticated ARM9 processor or better than that, is going to start going out of order, superscalar, and start issuing things in parallel. And then this assumption doesn't hold, and most analysis that has been done by the real-time community breaks down. There are very, very few works that generalize beyond this because it's hard. Another assumption that people like to make is that there's no cache in the system. And that one is going to be pretty hard for people to swallow. So people are now working around that assumption by saying, no, there is a cache, but it's either completely private or it's partitioned, so it appears to be private, because in that case, I don't have to include cache sharing in my analysis, also to make things easy. No cache might be hard to swallow. Partition caches, well, I guess it might be reasonable. It's at least it seems like an intuitive approach to deal with interference. So why not? This one also comes up, and that is when you compute the worst case execution time, your static analysis tool, if that's what you're using, is going to find the longest path through the program, and that's the worst case execution time. But when you start looking at resource interference, you also need to know where do I have the largest number of resource accesses, because those are the ones that are going to interfere with the other guys, and I need to compute how long these will take in the presence of other people. So you need to know that number, and of course the same tool that can tell you what's the longest path through the program can also tell you what's the path with the most memory accesses. That's no problem. The point is that these are typically different paths. And then in your analysis, what people have to do is to be conservative and say, well, I know I can't be on both these different paths at the same time, but I don't know which one I'm on, and I don't know what's going to be worse in total, quite frankly. So then they just overlap those and say, I assume the longest path, but I will assume that this path also has the maximum number of memory accesses on it, so they will take that number from a different path and pretend that happens on the longest path just to be conservative. And of course, that might be hysterically pessimistic. When it comes to looking at papers that are actually doing these things and the impact, all of this will happen in the system model. It's one line in assumptions. So even though you can have papers that make something 10 or 15% better, this assumption may already have made everything unreasonable. You don't know, because these are the underlying assumptions that we take for granted and that we never bother to evaluate. So that's something that would be interesting or very relevant going forward. For the rest, the community is thinking about how should we model things? How should we model memory accesses, for instance? Do we care about the total number of memory accesses per tasks or per super block or basic block, or is it fair to look at some kind of curve that talks about number of memory requests over time for any window, because that is a rich model. You have much more information if you know maximum and minimum over time, and when you have these curves, you all know we can do pretty cool stuff and cool analysis based on that. But of course, then the question is, where do you get all that information from? Which tool is it that you expect to provide you with that information from a complex multi-path program? And that is something that's on my mind sometimes, because to get good bounds, you need to have a lot of information, but good information is very difficult to get. So here's some good news, and this is something, instead of just whining about what's always difficult, this is something that seems to be working well. That's memory throttling. And that's becoming an increasingly popular way to control interference in memories. And the reason this is getting popular is because it's fairly easy. It's something you can implement in your operating system. Maybe it's 100 lines of code. And all you need to do it in your system is good performance monitoring counters. So you need to be able to have a counter that can measure how many memory accesses has this core issued, for instance. And that exists already in most platforms. And it's also something that the average case people love to have, because they can use this for profiling and for measurements, good for optimizing performance. So this is something that we want and they want, and because there's more of them than there is of us, this means that we may actually get what we want. So this is nice. So the basic idea of memory throttling is to say, well, how about if we assign memory access budgets? Maybe we do this to a core, or to a partition, or to tasks, or whatever it is we care about. And then during execution, we'll just monitor these counters to see how many are being issued. And when, for instance, a task runs out of its memory budget, we'll just suspend it. Even if it's not finished, we can preempt it and just wait for, it has to wait for its budget to be replenished before it can go again. So that's nice. That's a way to control how much someone may interfere. And there's been a couple of different suggestions for how to implement this. This is currently a hot topic, so there's maybe a couple of papers on this every year in the main real-time conferences. And some flavors that you see is how do we deal with Slack to make this efficient. And for instance, you can say, well, if everyone runs out of budget, then we can start distributing some Slack to improve the average case. Other people say, well, you know, if you can prove that there is Slack capacity in the system before everyone runs out, then you can start refilling them and no one ever has to really run out, and then no one has to ever be stalled, which might be more efficient. And there are just different ways to do this. Of course, now, if you start adding more budgets to your system, then you need to change your scheduling theory, because your normal vanilla flavored EDF is not going to be aware of memory budgets and that they will affect the response time and so on. So you need new analysis to be developed. And some people have already started looking at this, both for flat systems and for hierarchically scheduled systems. And that simply means starting to take these memory budgets into account, so like multi-resource servers and so on. When you're developing this analysis, then there will be some parameter in there that relates to the time it takes to make a memory access. And you all of a sudden need to know how long this takes. And people deal with this in different ways, by, for instance, saying, I assume it takes a time t, or I assume it takes 40 clock cycles because it's an integer. Or sometimes people measure and take the maximum, but rarely this is done using a validated model for a COT system, because it's really, really hard to validate models on COT systems. So what you can do if you get fed up with all this analytical modeling, because it's hard, is to be pragmatic and do the engineering solution and start measuring things. And there are tools for this as well, like from Rapida, they have the RapidTime tool that does worst-case execution time analysis by measurement. Of course, the question that always comes up is, when you measure, is it really going to be safe? And if you ask them, of course, they will say, sure. They say, we make sure we have good code coverage, all of that. They say, maybe it's hard to really, really, really guarantee every measurement. But then they say, well, what we do is we don't measure the whole program, every path. We measure many small pieces, many small paths. And then there's going to be some stitching process to take these small measurements and combine them and find out what the longest path is. And that stitching process is actually a little bit conservative, pessimistic. So maybe the total outcome is actually more likely, or maybe much more likely, to be in the pessimistic end than in the optimistic end. So they insist, of course, that their tool is safe. Another thing you can do is, if you want to know how long it takes to access a memory, because that might be input to some analysis indeed in many cases, you can also do that by measurement, but then of course you need to make sure that that resource is displaying worst case behavior during the measurement. And the trick then is to try to make some synthetic resource stressing benchmark where all cores is accessing a memory with the maximum aggressive pattern you can come up with, and all DMAs are doing their worst. It's hard to come up with what the worst case really is. But of course you can do your best and get measurements that are much larger than during execution and isolation. So that is something people are doing. Now, to move on and just say very, very few words about what the flow looks like in the Airbus approach. It looks fun when I say that this is the Airbus approach, because it's not true in the sense that this is not their approach to multi-cores that they have commercialized or used as internal process. This is done by Jan Novac, who was a PhD student in Airbus, and that was his PhD to do this. But I still think this is very interesting work to talk about, for the reason that it has a very nice and, I think, relevant setup. There's a Freescale P4080 multi-core platform with 8 cores. There's, in this particular part of the work, he used Cisco PikeOS, so it's a commercial operating system. For static analysis, he used AIT from Absinthe. And he used relevant benchmarks, or at least as relevant as they get. We used Embassy Automotive. There is no avionic benchmark, so well, you take what you get. And then the general approach that he's using is to split the timing analysis, split the total analysis into two parts. It's the individual core local analysis, and then dealing with interference analysis separately. So what that looks like is more or less you have your single core over there running an application, then you feed that an application binary. So this is the same flow you would use first for any single core. So then it will construct the control flow graph, it will analyze the control flow graph, it will have some model that captures the behavior of, in this case, the P4080, that prototype model developed by Absent, and do the path analysis and figure out what the worst case execution time is. So that would be the first part. And you do that for all the applications on all the cores in isolation. Then the second part is, that's the interference analysis, where you say, well, I will find the path through the program with the worst case number of resource accesses. So said before, there's probably a different path, but I will still use that number to be safe. And then for those memory accesses, well, this guy here, he has the most accesses of all. And when I analyze this guy, I know that I have 1,000 accesses. I know that this guy here next door, he only has 100. And that means that in the beginning, I assume everyone assumes can interfere with me. But after 100 accesses, I know that this guy just can't anymore because he ran out of accesses. So then I know there will be maximally 2 other cores interfering with me. And a little while later, I know that now this guy ran out. So now there can only be 1 other guy interfering with me. And then you get some extra information about the number of accesses into your bound. But you still see, this is exactly what we talked about before. This is one of these guys, or one of these approaches that says, I know nothing about the scheduler. It doesn't know what it does. I only know that there's differences in how many accesses we have, and that's the only thing that's being exploited. So it doesn't know the actual policy, and that the guy under analysis may be served really, really fast because, well, just don't know what sits in the hotspot. So he made some experiments saying that if you're executing in isolation for a bunch of these benchmarks, you get this kind of number. If you just assume that everyone is always interfering maximally with you, so for every request, all cores are interfering, you get this kind of execution times for your tasks. And if you're at least aware of this different budgets or different number of requests that they can issue, you're in this range, and this range is already a lot better than that range, and is not infinitely higher than that range. But of course, actual numbers will depend on the particular experimental setup. So since I haven't explained all the details of the setup to you, we're not going to spend too much time looking at numbers here, because then we may just generalize conclusions that aren't there. But he had nice numbers for this paper. Then for Slack, he has one of these methods based on proven Slack, where there is a computed bound and a computed response time, and then there are measurements happening during the execution of tasks. So for instance, when a task gets suspended after a while, you can look and say, well, how long have I executed? How many memory requests have I issued? Am I doing better than I expected that I would? So how much slack is there in the system? So you get a certain amount of time because things went better than worst case. You know how much spare time you've generated. And then if you know how long a memory access takes, you can turn that into new memory access budget and say, hey, we can afford 100 more accesses than we thought, and then these are being distributed out according to some policy to the different cores. So not waiting for all the budgets to deplete, but rather trying to check the worst case assumption versus actual state at certain points during execution to do better, which is an interesting way of doing it. And it's time to round off this presentation. So the story I've been telling you is about the increased integration and how that drives the transition to multi-core. And we have resource sharing that causes interference between applications, and in the avionics or the safety critical domains, you get a nightmare with respect to certification, where you need great isolation and interference mitigation techniques. Otherwise, your development time and development cost goes absolutely bananas. So it's difficult to isolate the sharing applications and to determine the worst case execution times. You can try to solve this using hardware. People built it, people showed it, but it's difficult to get commercial uptake for time predictable hardware. What is happening in most cases is that people get COD systems, and this is something that the community has been spending a lot of time on trying to analyze. But there is, of course, problems because coming up with models is very, very hard. If you don't have very direct connections directly to the vendors, you sign an NDA and you start to get good information. Probably for companies that are actually trying to build an airplane or build a car, they will have those relations, they will sign those contracts, and they will get help that they need. But a problem is for us as researchers who are supposed to pave the way for this to some extent and to come up with methods, well, we can't really help them out as concretely as we would like because of the lacking openness. We can't make models and validate and show that they're relevant. Yeah. And that's what we're trying to do. So we're looking at the right models, trying to find the right abstractions. The main problem that I want to flag is that it's fun to come up with models, but they're not very useful unless there's some way to show that they relate to an implementation, either a simulator or a hardware implementation. And if it's just too hard to make models, then maybe we should just start measuring instead, because then at least we can measure our way around some of these showstopper kind of problems that we have with modeling. And that's the end of my presentation. Thank you all for coming. If you have any questions, I'm happy to go.